Hello there, and welcome to this quiet corner of the internet, where science gets soft-spoken and curiosity wraps itself in a warm blanket. Tonight, we're embarking on a gentle journey through one of the most profound stories our planet has ever told, the story of climate change and global warming. It's a tale that unfolds over centuries and decades, written in ice cores and tree rings, told through the whispers of melting glaciers and the patient observations of scientists around the world. If you're settling in for the evening, perhaps with a cup of tea cooling on your bedside table, or maybe you're just trying to wind down after a day filled with too many notifications and not enough quiet moments, you've come to the right place. This isn't a story designed to alarm or overwhelm. It's a story meant to inform and hopefully to soothe, because understanding our changing climate, really understanding it, can be both humbling and oddly comforting in its own way. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing a little more about the beautiful, complex system that is Earth's climate. Before we begin this slow voyage through atmospheric science and planetary rhythms, if you find these gentle explorations helpful for relaxation or learning, I'd be grateful if you gave this video a like, subscribed, or simply left a comment letting me know where in the world you're listening from tonight. It's always wonderful to know that these words are finding their way to curious minds across different time zones and seasons. So, take a deep breath. Feel that air filling your lungs, a mixture of nitrogen and oxygen that has been cycling through our atmosphere for millions of years. Let your shoulders relax, and let's begin this quiet exploration of how our planet's climate has changed, is changing, and continues to change in ways both subtle and profound. The gentle breath of Earth. Imagine, if you will, that Earth has lungs, not literal lungs, of course, but something far more elegant and complex, an atmospheric system that breathes in and out over seasons, years, and millennia. This breathing is what we call climate, and it's been going on for about 4.6 billion years, ever since our planet first gathered enough dust and gas to call itself a world. But what exactly is climate? It's easy to confuse it with weather, that immediate changeable thing that decides whether you'll need an umbrella today, or if you can wear that light jacket you've been eyeing. Weather is the day-to-day mood of the atmosphere, fickle and immediate. Climate, however, is the long-term personality of the atmosphere, the average of weather patterns stretched across decades and centuries. Think of it this way. If weather is a single page in a very long book, climate is the entire story. It's the overall arc, the underlying themes, the way characters develop and change over time. And what a story it is, full of ice ages and warming periods, volcanic winters and greenhouse springs, all playing out over timescales that make human lifespans seem like brief flickers. For most of its existence, Earth's climate has been remarkably stable in some ways, and wildly variable in others. There have been periods when ice covered much of the planet, turning it into something resembling a cosmic snowball. There have been other times when the polar regions were so warm that palm trees grew where polar bears roam today. The planet has experimented with different atmospheric compositions, different ocean currents, different arrangements of continents, each configuration creating its own climate signature. But here's what makes our current moment in this vast story so remarkable. For the first time in Earth's history, a single species, us, has become powerful enough to significantly alter the planet's climate system. It's a responsibility we stumbled into gradually, almost accidentally, like a child who suddenly realizes they're tall enough to reach the thermostat and strong enough to actually turn it. The atmosphere that surrounds us, that invisible ocean of gas we swim through every day, is surprisingly thin. If Earth were an apple, the atmosphere would be thinner than the apple's skin. And yet, within this delicate shell, an intricate dance of molecules determines whether ice sheets advance or retreat, whether deserts bloom or expand, whether coastal cities stand tall or slowly sink beneath rising seas. This atmospheric dance is choreographed by what we call the greenhouse effect, and it's one of the most important and misunderstood processes on our planet. The name itself can be misleading. It conjures images of glass structures in botanical gardens, humid and artificial, But the atmospheric greenhouse effect is neither artificial nor necessarily problematic. In fact, without it, Earth would be a frozen wasteland with an average temperature of about -18 degrees Celsius or 0 degrees Fahrenheit. Life as we know it simply wouldn't exist. Here's how it works. Gently and continuously, sunlight streams down from our nearest star, carrying energy across 93 million miles of space. When this energy reaches Earth's atmosphere, some of it is reflected back to space by clouds and ice and other bright surfaces. But much of it passes through the atmosphere and warms the planet's surface, the land, the oceans, the forests, the cities. Now, like any warm object, Earth radiates heat back toward space. But this outgoing energy is different from the incoming sunlight. It's what we call long-wave radiation, invisible to our eyes but perfectly real nonetheless. And here's where the greenhouse effect comes in. Certain gases in the atmosphere, water vapor, carbon dioxide, methane and others, are very good at absorbing this long-wave radiation. They catch it, hold onto it for a moment, and then re-radiate it in all directions, including back down toward Earth's surface. It's a bit like wrapping yourself in a blanket. The blanket doesn't generate heat, but it traps the warmth your body produces, keeping you comfortable through the night. The greenhouse gases in our atmosphere work in much the same way, creating a warming effect that keeps our planet at temperatures suitable for liquid water, growing seasons, and the rich tapestry of life we see around us. For thousands of years, this system hummed along in relative balance. The concentration of greenhouse gases in the atmosphere fluctuated naturally. Ice ages came and went. Volcanic eruptions temporarily cooled the planet. Ocean currents shifted and brought changes to regional climates. But overall, the system remained within a range that allowed human civilization to develop and thrive. And then, quite recently in geological terms, something began to change. Humans discovered fossil fuels, coal, oil, and natural gas, and learned to release the energy stored in these ancient deposits of organic matter. We began to power our societies with the carbon that had been locked away underground for millions of years, effectively taking carbon from the deep past and adding it to the present-day atmosphere. At first, the changes were subtle, barely detectable against the natural variability of Earth's climate system, but gradually, decade by decade, the signal began to emerge from the noise. The concentration of carbon dioxide in the atmosphere started to rise, slowly at first, then more rapidly, and as it rose, so did global temperatures. This is the heart of the climate change story we're living through today. It's not a story of malice or deliberate harm, but rather one of unintended consequences, a species that grew powerful enough to alter planetary systems before fully understanding what those systems were or how they worked. It's a story that began in earnest with the Industrial Revolution about 250 years ago, but really accelerated in the decades following World War II, when human population, energy use, and industrial activity all began to grow exponentially. But let's not get ahead of ourselves. To really understand where we are today, we need to go back much further to see how Earth's climate has changed naturally over vast stretches of time, because only by understanding the planet's climatic past can we fully appreciate the significance of what's happening in the present and what might unfold in the future. The story begins, as all good stories do, with the formation of Earth itself. The ancient rhythms, 4.5 billion years ago, give or take a few million, our planet was a very different place. Imagine a world of molten rock and toxic gases, bombarded by asteroids and comets, with an atmosphere so thick and hot, it would make Venus seem pleasant by comparison. There were no oceans, no continents as we know them, and certainly no life. Earth was still in its infancy, learning how to be a planet. But even then, climate was shaping the world. The early atmosphere, composed mainly of hydrogen and helium, was gradually stripped away by solar winds and replaced by gases released from volcanic activity, water vapor, carbon dioxide, nitrogen, and trace amounts of other compounds. As the planet slowly cooled, water vapor began to condense, falling as rain that may have lasted for millions of years, gradually filling the basins that would become our first oceans. This was Earth's first great climate event, and it set the stage for everything that followed. The formation of oceans not only provided a medium for life to eventually emerge, but also created a massive system for storing and circulating heat around the planet. Ocean currents began to flow, carrying warm water toward the poles and cold water toward the equator. Then, somewhere around 3.8 billion years ago, life appeared. At first it was simple, single-celled organisms that could survive in what we would consider extremely harsh conditions. But these early life forms were already beginning to interact with the climate system in profound ways. Some of them learned to use sunlight to convert carbon dioxide and water into organic compounds, the process we call photosynthesis, and as a byproduct of this process, they released oxygen into the atmosphere. This was revolutionary. Oxygen, which we now think of as essential for life, was actually toxic to most of the organisms that existed at the time. Its accumulation in the atmosphere triggered what scientists call the Great Oxidation Event, about 2.4 billion years ago. It was Earth's first major extinction event, but also its first great transformation. The oxygen released by these early life forms gradually changed the chemistry of the atmosphere and oceans, paving the way for more complex forms of life that could use oxygen for energy. Over the following billions of years, life and climate continued to evolve together in an intricate dance. Ice ages came and went with a rhythm that seems to be influenced by subtle changes in Earth's orbit around the Sun. These orbital cycles, discovered by the Serbian mathematician Milutin Milankovic in the early 20th century, occur over periods of tens of thousands to hundreds of thousands of years. As Earth's orbit becomes more or less circular, as its axis tilts at different angles, and as its axis wobbles like a spinning top, the amount and distribution of solar energy reaching different parts of the planet changes slightly. These small changes in solar energy might seem insignificant, but they can trigger much larger changes in the climate system through a process called feedback. For example, if orbital cycles cause ice sheets to grow larger, the white ice reflects more sunlight back to space, which cools the planet further, which allows ice sheets to grow even larger. It's a self-reinforcing cycle that can push the climate system from one stable state to another. The geological record tells us that Earth has experienced major ice ages roughly every 150 million years or so, with smaller-scale glaciations occurring much more frequently. During the most recent series of ice ages, which began about 2.6 million years ago, ice sheets repeatedly advanced and retreated across northern continents. At the peak of the last ice age, about 20,000 years ago, ice covered much of North America and northern Europe. Sea levels were about 400 feet lower than today, and the global average temperature was about 6 degrees Celsius colder than it is now. But Earth's climate history isn't just a story of ice ages. There have also been periods of exceptional warmth. During the Paleocene thermal maximum, about 56 million years ago, global temperatures were perhaps 8 degrees Celsius warmer than today. Arctic regions were ice-free, and palm trees grew in Alaska and Antarctica. This warming event was likely triggered by the release of huge amounts of carbon dioxide and methane into the atmosphere, possibly from volcanic activity, or from the destabilization of marine methane deposits. What's particularly interesting about this ancient warming event is how long it took to unfold and how long it took for the climate system to recover. The initial warming happened over several thousand years, extremely rapid in geological terms, but slow compared to the changes we're seeing today. And it took hundreds of thousands of years for global temperatures to return to their previous levels, as the excess carbon was gradually removed from the atmosphere through natural processes like rock weathering and burial of organic matter in ocean sediments. These natural climate changes of the past were driven by forces that operated on vast timescales: the slow dance of continents as they drifted across Earth's surface, the gradual brightening of the sun as it aged, massive volcanic eruptions that could alter atmospheric composition for decades or centuries, and the orbital cycles that shifted the planet's relationship with solar energy. Throughout all of these changes, life adapted and evolved. Species migrated as climate zones shifted. evolved new strategies for surviving in changing conditions, or went extinct when they couldn't keep pace with environmental changes. But life also influenced climate in return. The oxygen in our atmosphere exists only because of photosynthesis. The carbon dioxide levels that have characterized much of Earth's history were regulated partly by the burial and exposure of organic matter. Even the formation of limestone, one of the most common rocks on Earth, is largely a biological process that removes carbon dioxide from the atmosphere and stores it in solid form. This is the crucial insight from Earth's climate history. Climate and life are not separate systems, but deeply interconnected parts of a single complex planetary system. Changes in one inevitably lead to changes in the other, sometimes gradually, sometimes quite rapidly. And so we arrive at the present moment in this vast story. A moment when one particular species has become so numerous and so energy-intensive that its activities have begun to rival natural geological and astronomical forces in their impact on global climate. We've become, in the words of some scientists, a geological force in our own right. But to understand how we got here, we need to look more closely at the particular time period that set the stage for our current climate crisis, the Little Ice Age and the warming that followed. The Little Ice Age and the dawn of change. If you had lived in Europe during the 17th century, you might have walked across frozen rivers that today never freeze. You might have seen glaciers creeping down mountain valleys where now there are only meadows. You would have experienced longer, harsher winters and shorter, cooler summers. Crop failures would have been common, and famine a constant threat. This was the Little Ice Age, not a true ice age in the geological sense, but a period of notably cooler temperatures that lasted roughly from 1300 to 1850. The Little Ice Age wasn't a single dramatic event, but rather a series of cooling episodes punctuated by milder intervals. Its causes were likely multiple reduced solar output during periods of low sunspot activity, increased volcanic activity that injected light-reflecting particles into the atmosphere, and changes in ocean circulation patterns. The overall cooling was modest by geological standards. Global temperatures dropped by perhaps 1 to 2 degrees Celsius, but the effects on human societies were profound. Glaciers advanced throughout the Alps and Scandinavia. The Thames River in London froze solid regularly, supporting famous frost fairs where merchants set up shops and revelers danced on the ice. In North America, the Hudson River froze as far south as New York City. Growing seasons shortened, wine production retreated southward, and agricultural communities struggled to adapt to the cooler conditions. But the Little Ice Age is important to our story not just because it demonstrates how sensitive human societies can be to relatively small changes in climate, but also because of what came next. Even as natural factors were cooling the planet, human activities were beginning to push in the opposite direction. The Industrial Revolution began in Britain in the mid-18th century. Powered by coal, ancient forests compressed and transformed over millions of years into concentrated energy. For the first time in human history, we began to use fossil fuels on a large scale to power machinery, heat homes, and fuel economic growth. Coal-burning factories, steam engines, and heating systems all released carbon dioxide into the atmosphere, carbon that had been stored underground for vast stretches of geological time. At first, the impact was local and barely detectable on a global scale, but the industrial model proved so successful at generating wealth and improving living standards that it spread rapidly to other parts of the world. By the mid-19th century, the United States was industrializing rapidly. By the early 20th century, Japan and much of Europe had followed suit. Each new industrial economy added to the cumulative emissions of greenhouse gases. The early scientists who studied these changes were remarkably prescient. In 1824, the French mathematician Joseph Fourier was the first to describe the greenhouse effect, recognizing that Earth's atmosphere traps heat in much the same way as glass in a greenhouse. In the 1850s, the Irish physicist John Tyndall demonstrated that water vapor and carbon dioxide in the atmosphere could absorb and emit heat radiation, and in 1896, The Swedish chemist Svante Arrhenius calculated that doubling the amount of carbon dioxide in the atmosphere would warm the planet by several degrees Celsius. Arrhenius actually viewed this prospect optimistically, suggesting that the warming effect of increased carbon dioxide might help prevent future ice ages and make northern regions more suitable for agriculture. He estimated that it would take about 3,000 years for human activities to double atmospheric carbon dioxide concentrations. He was off by more than a factor of 10. We're likely to reach that doubling within the next few decades, less than 300 years after the beginning of the Industrial Revolution. The acceleration happened gradually at first, then more rapidly. The two world wars spurred technological development and industrial production. The post-war economic boom of the 1950s and 1960s brought unprecedented prosperity to much of the developed world, along with a massive increase in energy consumption. The Green Revolution in agriculture fed growing populations but relied heavily on fossil fuel-derived fertilizers and mechanization. Globalization connected economies around the world, but also increased transportation-related emissions. Meanwhile, scientists were beginning to detect the first clear signals of human influence on the global climate system. In the 1950s, Charles David Keeling began making precise measurements of carbon dioxide concentrations at a remote observatory on Mauna Loa in Hawaii. His measurements, which continue to this day, showed an unmistakable upward trend in atmospheric carbon dioxide, rising from about 315 parts per million in the late 1950s to over 420 parts per million today. The Keeling curve, as this record came to be known, was one of the first pieces of definitive evidence that human activities were altering the composition of the atmosphere on a global scale. But carbon dioxide concentrations were just one piece of a much larger puzzle. Scientists were also documenting changes in global temperatures, sea levels, ice coverage, precipitation patterns, and the timing of seasonal events like flowering and migration. By the 1970s, it was becoming clear that the Little Ice Age was definitively over. Global temperatures had been rising steadily since the mid-19th century, with the warming accelerating in recent decades. The last glacial ice was retreating from valleys where it had persisted for centuries. Sea levels were beginning to rise as ocean water expanded with warming and land-based ice began to melt. The signs of a changing climate were becoming too numerous and too consistent to ignore. But understanding that the climate was changing was only the beginning. The much harder question was figuring out why it was changing, how much human activities were contributing, and what might happen in the future. This required not just careful observations of the present-day climate system, but also a deep understanding of how that system had behaved in the past and how it might respond to continued human influences. And so we come to one of the most remarkable detective stories in the history of science, the effort to understand Earth's climate history and use that understanding to peer into our climatic future. Reading the Climate Chronicles. Imagine trying to reconstruct a story from fragments scattered across time and space, a page from a diary buried in Antarctic ice, a chapter written in the rings of an ancient tree, a paragraph dissolved in ocean sediments, a sentence trapped in coral formations. This is the challenge that climate scientists have taken on, reading Earth's climate history from the archives that nature herself has been keeping for millions of years. These natural archives, called paleoclimate records, are remarkably detailed and surprisingly abundant once you know where to look. Every year, snow falls on polar ice sheets and gradually compresses into ice, trapping tiny bubbles of ancient atmosphere. Every growing season, trees add a new ring of wood, with the thickness and cellular structure of each ring reflecting the temperature and moisture conditions of that particular year. In the depths of the ocean, microscopic organisms live, die, and sink to the seafloor, their shells preserving chemical signatures of past ocean conditions. Each of these archives tells a slightly different part of the story, covering different time periods and recording different aspects of the climate system. Together, they create a remarkably detailed picture of how Earth's climate has changed over the past several 100,000 years, with some records extending back millions of years. The ice cores from Antarctica and Greenland are perhaps the most famous and detailed of these climate archives. When scientists drill into these ancient ice sheets, they're essentially creating a timeline that stretches back in some cases more than 800,000 years. The ice itself records past temperatures through subtle changes in the isotopic composition of the water molecules. The tiny air bubbles trapped in the ice preserve samples of ancient atmospheres, allowing scientists to measure past concentrations of carbon dioxide, methane, and other greenhouse gases with remarkable precision. What these ice cores reveal is both reassuring and deeply concerning. On one hand, they confirm that Earth's climate system is capable of dramatic changes over relatively short periods. The transition from ice age to interglacial conditions, for instance, involved global temperature changes of 6 degrees Celsius or more, often occurring over just a few centuries or decades. On the other hand, they show that for the past 10,000 years, essentially the entire period of human agriculture and civilization, the climate has been remarkably stable compared to earlier periods. This stability wasn't accidental. During the past 10,000 years, atmospheric carbon dioxide concentrations remained within a fairly narrow range, fluctuating between about 260 and 280 parts per million. Global temperatures, while varying from region to region and decade to decade, remained within a range that allowed ice sheets to persist, sea levels to remain relatively constant, and agricultural systems to develop and spread around the world. Tree ring records, which can extend back several thousand years in some regions, provide even more detailed information about climate variability during this stable period. They reveal that even within this overall stability, there were significant regional and multi-decade variations. The medieval warm period from roughly 950 to 1250 CE brought warmer conditions to much of the North Atlantic region, allowing Vikings to establish settlements in Greenland and briefly in North America. The Little Ice Age that followed brought cooler conditions, shorter growing seasons, and advancing glaciers to many parts of the world. But even the most extreme of these natural variations pale in comparison to what has happened since the mid-19th century. The ice core record shows that current carbon dioxide concentrations are higher than at any time in at least 800,000 years, and probably much longer. The rate of increase, about 2.5 parts per million per year in recent decades, is roughly 100 times faster than the most rapid natural variations recorded in the ice cores. Ocean sediment records, which can extend back millions of years, provide an even longer-term perspective on climate change. These records show that Earth has experienced periods of much higher carbon dioxide concentrations and temperatures in the distant past, but also that these changes typically occurred over time scales of thousands to millions of years, not decades. The sediment records also reveal something crucial about how the climate system responds to increases in greenhouse gases. During past periods of high carbon dioxide, global temperatures were indeed much higher than today. Ice sheets were smaller or absent altogether, and sea levels were tens of meters higher than at present. These past conditions suggest that if we continue to increase greenhouse gas concentrations, the climate system will eventually respond with similarly dramatic changes. But there's an important lag in the system. Even when greenhouse gas concentrations change rapidly, the full climate response can take decades to centuries to unfold. This is partly because the oceans, which store vast amounts of heat, warm and cool slowly. Ice sheets, which can hold enough water to raise sea levels by tens of meters, also respond slowly to temperature changes. What this means is that we're already committed to a certain amount of additional warming and sea level rise based on the greenhouse gases we've already emitted, even if we were to stop all emissions immediately. Coral reefs provide another important climate archive, particularly for tropical ocean conditions. Corals build their skeletons from calcium carbonate, extracted from seawater, and the chemical composition of these skeletons reflects the temperature and chemistry of the water in which they grew. Some coral records extend back several centuries and provide detailed information about sea surface temperatures, ocean acidity, and the frequency and intensity of events like El Niño. These coral records are particularly important because they document changes in ocean conditions and the oceans play a crucial role in regulating Earth's climate. The oceans absorb about 30% of the carbon dioxide that humans release into the atmosphere, helping to slow the rate of climate change, but also making the oceans more acidic. They also absorb more than 90% of the excess heat that greenhouse gases trap in the climate system, causing sea levels to rise as the water expands and creating new patterns of ocean circulation. What emerges from all of these natural archives is a picture of a climate system that is both remarkably stable over long periods and capable of dramatic rapid changes when pushed beyond certain thresholds. The records show that small changes in external forces, like variations in solar output or atmospheric composition, can sometimes trigger much larger changes in climate through feedback processes that amplify the initial change. This is perhaps the most important insight from the paleoclimate record. The climate system has tipping points, conditions beyond which self-reinforcing feedback processes take over and drive additional changes, even without further external forcing. We see evidence of this in the rapid transitions between ice age and interglacial conditions, in the abrupt changes in ocean circulation recorded in marine sediments, and in the dramatic vegetation shifts documented in pollen records. The question that keeps climate scientists awake at night is whether we're approaching similar tipping points in today's climate system. Are we pushing the system toward a threshold beyond which change becomes self-sustaining and irreversible? The paleoclimate record suggests that such thresholds exist, but it also shows that the climate system can remain stable for long periods when conditions are right. Understanding these past changes is crucial not just for satisfying scientific curiosity, but for predicting how the climate system might respond to continued human influences. The past is not just prologue, it's also our best guide to possible futures, and what it tells us is both sobering and urgent. The climate system can change rapidly when pushed hard enough, and some of those changes can persist for millennia even after the original cause has been removed. But the paleoclimate record is just one tool in the climate scientist's toolkit. To really understand what's happening to our climate today, we also need to monitor the present-day climate system in exquisite detail, looking for the signals of change amid the noise of natural variability. The Great Acceleration. If you were to plot the major indicators of human impact on Earth's systems, population, economic growth, energy use, greenhouse gas emissions, the resulting graph would show a gentle rise for most of human history, followed by a dramatic upward surge beginning around 1950. Scientists call this period the Great Acceleration, and it represents the most rapid transformation of planetary conditions in human history, possibly in Earth's history. The numbers are staggering in their scope and scale. Human population, which took most of human existence to reach 1.6 billion in 1900, tripled to nearly 5 billion by 1990, and has continued growing to nearly 8 billion today. Energy consumption increased even more dramatically, rising roughly 12-fold since 1900. The production of cement, a major source of carbon dioxide emissions, increased more than 20-fold. The use of fertilizers, which require enormous amounts of energy to produce, increased nearly 50-fold. But perhaps most significantly for our climate story, carbon dioxide emissions from fossil fuel burning increased from about 1 billion tons per year in 1900 to over 35 billion tons per year today. This represents not just a quantitative change but a qualitative transformation in humanity's relationship with planetary systems. During this period, the signals of human influence on climate began to emerge clearly from the background noise of natural variability. Global average temperatures, which had been rising gradually since the mid-19th century, began to increase more rapidly. The warming wasn't uniform. Some regions warmed more than others, some seasons more than others, but the overall trend became unmistakable. The Arctic has experienced some of the most dramatic changes. Arctic temperatures have risen about twice as fast as the global average, a phenomenon known as Arctic amplification. This occurs because, as ice and snow melt, they're replaced by darker surfaces that absorb more solar energy, creating a feedback loop that accelerates warming. Arctic sea ice, has declined by about 13% per decade since satellite measurements began in the late 1970s. The Greenland ice sheet is losing mass at an accelerating rate. Permafrost, permanently frozen soil that stores vast amounts of carbon, is beginning to thaw across large regions of the Arctic. These changes have cascading effects throughout the climate system. As ice reflects sunlight back to space, the loss of ice means more solar energy is absorbed by the planet, contributing to further warming. As permafrost thaws, it releases carbon dioxide and methane that had been locked away for thousands of years, adding to the greenhouse gases in the atmosphere. As ocean water warms and expands, and as land-based ice melts, sea levels rise. The oceans themselves are changing in profound ways. Not only are they warming, the top 2,000 meters of the ocean have warmed by about 0.4 degrees Celsius since the 1970s, but they're also becoming more acidic as they absorb carbon dioxide from the atmosphere. Ocean acidity has increased by about 30% since the beginning of the Industrial Revolution, affecting marine organisms that build shells and skeletons from calcium carbonate. Changes in precipitation patterns are becoming increasingly evident as well. While global average precipitation has increased slightly as a warming atmosphere holds more moisture, the distribution of that precipitation is shifting. Some regions are becoming wetter, others drier. Many areas are experiencing more intense rainfall events, leading to increased flooding, while others are facing more severe and persistent droughts. The timing of seasonal events is shifting too. Spring is arriving earlier in many parts of the world, as evidenced by earlier flowering of plants, earlier migration of birds, and earlier melting of snow and ice. These phenological changes, as they're called, might seem minor, but they can disrupt ecological relationships that evolved over thousands of years. Perhaps most ominously, the frequency and intensity of extreme weather events appears to be increasing. Heat waves are becoming more common and more severe. Droughts are lasting longer and covering larger areas. Hurricanes and typhoons, while not necessarily more frequent, are intensifying more rapidly and maintaining their intensity longer. Wildfire seasons are extending, and fire behavior is becoming more extreme. All of these changes are occurring against the backdrop of an atmosphere that is changing composition more rapidly than at any time in human history. Carbon dioxide concentrations, measured continuously at sites around the world since the late 1950s, have risen from about 315 parts per million to over 420 parts per million today. This represents an increase of more than 30% in just over 6 decades. But carbon dioxide isn't the only greenhouse gas increasing in concentration. Methane, which is more than 25 times more potent than carbon dioxide at trapping heat over a 100-year period, has more than doubled since pre-industrial times. Nitrous oxide has increased by about 20%, and there are entirely new greenhouse gases in the atmosphere, synthetic compounds like hydrofluorocarbons that didn't exist in nature and are thousands of times more potent than carbon dioxide. The evidence for human influence on the climate system has become so overwhelming that scientists now speak with remarkable confidence about the reality of human-caused climate change. Multiple independent lines of evidence all point in the same direction. Human activities, particularly the burning of fossil fuels, are the primary driver of observed climate change since the mid-20th century. This confidence comes not just from the observational evidence, but also from sophisticated climate models that can simulate the behavior of the climate system under different conditions. When these models are run with natural factors alone, solar variations, volcanic eruptions, natural cycles, they cannot reproduce the warming observed since the mid-20th century. But when human influences are included, particularly greenhouse gas emissions, the models accurately reproduce both the magnitude and the pattern of observed warming. The models also project continued warming in the coming decades and centuries, with the amount of warming depending critically on how much additional greenhouse gases we emit. Under scenarios with continued high emissions, global temperatures could rise by 3–5 degrees Celsius or more by the end of this century. Under scenarios with rapid reductions in emissions, warming could be limited to 1.5-2 degrees Celsius above pre-industrial levels. These might seem like small numbers, but in the context of the global climate system, they represent enormous changes. To put this in perspective, the difference between today's climate and the depths of the last ice age is only about 6 degrees Celsius. A warming of 3-5 degrees would create a climate unlike anything in human history. But the Great Acceleration isn't just a story of changes that have already occurred. It's also a story about the recognition of those changes and the growing understanding of what they mean for the future. As the evidence for human influence on climate has mounted, so too has awareness of the issue among scientists, policymakers, and the general public. The scientists speak. In the summer of 1965, a group of scientists gathered at a conference at the Woods Hole Oceanographic Institution in Massachusetts to discuss what was then called the CO2 problem. Among them was Charles David Keeling, whose measurements from Mauna Loa had already documented the relentless rise in atmospheric carbon dioxide. The question they wrestled with was not whether human activities were changing the atmosphere, that was already clear, but what the consequences might be. Their report, delivered to President Lyndon Johnson later that year, contained a remarkably prescient warning. By the year 2000, they wrote, the increase in atmospheric CO2 will be close to 25%. This may be sufficient to produce measurable and perhaps marked changes in climate. They suggested that the melting of Antarctic ice could raise sea levels significantly, and they noted that the climatic changes that may be produced by the increased CO2 content could be deleterious from the point of view of human beings. This was perhaps the first official government recognition of what would later become known as global warming or climate change, but it would be many years before the scientific community reached a consensus on the issue, and even longer before that consensus began to translate into policy action. Throughout the 1970s and 1980s, climate scientists continued to piece together the evidence for human influence on the climate system. They developed increasingly sophisticated computer models that could simulate the complex interactions between the atmosphere, oceans, ice sheets, and land surface. They deployed networks of monitoring stations to track changes in temperature, precipitation, and atmospheric composition around the world. They drilled ice cores from Antarctica and Greenland, cored lake sediments and ocean floors, and analyzed tree rings to reconstruct past climate conditions. The work was painstaking and often contentious. Climate is naturally variable, and distinguishing the signal of human influence from the noise of natural fluctuations required decades of careful observation and analysis. Different research groups sometimes reached different conclusions. Models disagreed on details, even when they agreed on the broad pattern of future warming. But gradually, the evidence accumulated, and the consensus strengthened.